This video is about correlation. It's not a substitute for the material that's in chapter 4 of the book because there's a lot more detail there. But I want to go over the basic ideas involved with correlating inputs because correlation is an important aspect of analyzing uncertainty. So let's go over first the basic method, or a few alternative methods of introducing correlation. Let's say we have two inputs here. We have a uniform distribution ranging from 0 to 5, and we have another risk uniform ranging from 0 to 5. And if they're independent of each other, which is what's happening here if I just put them in, as soon as you randomize, you just get two different values ranging from 0 to 5, and every time you press F9, that's the way they'll come out. You could also run a simulation. And if you want to look at what the two outputs look like, here's a scatter plot of the two versus each other, and they're randomly scattered, both ranging from 0 to 5, no correlation. Now let's say you wanted to correlate them. So one method, if you've entered the distributions in your spreadsheet already, and now you want to correlate them, is to highlight the two, go to define correlations, and say define copular. By highlighting them ahead of time and putting defined copula, you get this dialog that shows a scatter plot of the two. It shows the two separate distributions. That cell A1 versus itself is going to be somewhere between 0 and 5, and the same thing for 2. But 1 versus 2, it shows a picture, but this is for a particular kind of copula. And I'll talk about these different types soon, but the most common type, and if you're familiar with the concept of correlation, what you're used to looking at is what is called in that risk a Gaussian copula. And that's a measure of linear correlation the correlation to 0.6. Now you start seeing that they tend to not be quite as random, not filling in that whole quadrant. They're kind of looking more in an upward shape. If you go to 0.8, now you can start seeing that there's definitely some relationship between the two. 0.9, even more. Now it's really closely correlated. You can go to 1. They're perfectly correlated, which means that a low value of one, you'll get a low value of the other. Technically, it's more correlated than that. It's saying if you look at the 10th percentile of the first distribution, you'll also be looking at the 10th percentile of the second distribution. Or if you're looking at the minimum value in the first, you'll be looking at the minimum value in the second. That's perfect linear correlation. Of course, these can also be negative. You can go the opposite direction. Let's just put in a different value right now, 0.8. So let's say you want to correlate them with 0.8. You can click OK. It wants to know where to put this copula, and I'm going to put it in a different part of the spreadsheet. Let's click on A4. I've just entered correlating these two inputs using, now this whole section that's been inserted. If you click on A4, this is the name of the copula. You can rename it, you can change its name. It's called copula 1 right now. What type? It's called a Gaussian copula. There are other types. And here's a matrix of the correlations. Everything always on the diagonal is perfectly correlated with itself, and there's a 0.8 correlation between them that's showing here. You can actually change, and so the other place that this shows up, this is the correlation that this just describes or defines the correlation, but this is what applies to correlation. If you look at the input distributions I put in, automatically it has added risk copula, which is a function. It gives a name of the copula, and the (1) is saying use the first. This distribution is the first of the two distributions that are correlated using this copula. On the second one, it also says risk copula, same name, but position 2. If you want to be perfectly correlated, you could change right here that to a 1. Now, one thing I've discovered that is a little odd, and I actually think it's kind of a bug that should be fixed, is if you press F9, you actually don't see this correlation taking place. I would have expected to see these numbers equal to each other, and they're not. They're still varying independently. But if you want to see what happens if you run a simulation, click on the scatter plot. Let's look at both of these cells. They are perfectly correlated. In fact, if you change from the statistics grid to the data grid, these are the 10,000 simulated values. You'll see on each line, both distributions had exactly the same values. So that's because they're perfectly correlated. It has imposed that when it randomly picks from the uniform distribution for A1, it's picking randomly the same exact value in this case for A2, because A1 and A2 are the same distribution, both uniform distributions from 0 to 5. The thing that seems a little strange about this is even though it used the same values for all 10,000 simulations, when you do F9, it doesn't show up in cell A1 and A2. The F9 key seems to be these varying independently. So at least my understanding is that the copula is only applied to the simulation when you run the simulation. The F9 key will not let you see the correlation pattern showing up in these two cells. So with F9, they're independent of each other, but when you run them, in fact, this has imposed perfect correlation. If you weaken this correlation to like 0.8, run it again. Click the scatter plot, look at these two. A little hard to see, but actually I think one thing you can do is, I think you can, I thought there's a way to drag it out to look at it a little bigger. I guess you can do that by zooming in. It's not so easy to tell, but you'll notice it's sparser up in the top left and the bottom right, which is an indication that there is correlation here. But even a correlation of 0.8 is far from perfect, but it will definitely make them related to each other. And if you look at the data grid here, oh, you can go back to the scatter plot. Go to the data grid. They're not the same values anymore, but you'll notice that A2, this was a relatively low value, less than 1. It was also less than 1 on the second. It's kind of middle range, 3.4, 2.7. There will be some varies where in the third one, it shows a low value for A2, but actually an above average value for A1. There will happen because the correlation was only 0.8 here. But in general, they're sort of lined up. Look at 10, which is at near the bottom of the distribution, and for both A1 and A2. So both of those are quite low. So the correlation pattern is picked up by doing it this way. So look at the way it was entered. I put in the distributions first, highlighted them, went to define correlations, and chose the Gaussian copula, inserted it in the spreadsheet, and it automatically attached them to the distributions. Here's an alternate way you could do it. You could go and define contribution, correlations. You could define a copula at this page. Let's say you want it to be a Gaussian copula. Let's say you wanted this to be 0.8. Notice it's automatically imposing 0.8 on the correlation between 1 and 2 can't be the difference between the correlation of 2 and 1. So it automatically imposes the same value there. You can attach it to distributions now by launching this, and you could say attach attach more inputs. You could attach it to these two and say replace, because I didn't have any inputs attached. Notice now it puts in A1 and A2 as the two distributions to attach it to. And where do you want the copula to appear? And it's the same thing. So what I did here is start by entering the copula and using the attachment editor to attach it. And it now is using copula 2 to attach. I replaced what was there, which was copula 1, is now replaced it with this copula 2. I could achieve the same thing the following way. I could go ahead and define a correlation matrix. And let's pick a place for it. We'll put it there. There are a lot of subtle details. You can look at the manual to see about instances and other things that you can do with it. But the basics in order to get this to work is the correlation matrix is set up right now with 1s on the diagonal and 0s. So if here you could put 0.8 in there. And notice it has also put 0.8 down here. You can add inputs here and attach it to those two. Click OK. This looks very similar in terms of the matrix, but it's a little bit different. The top left does not say risk copula, it says risk correlation matrix. Up here, it replaced what was a risk copula with a risk correlation matrix. The name of the matrix, and again, comma 1 means this is the first of the two distributions. The comma 2 means use this in the second of the two distributions. The only difference between the correlation matrix and the copula is the correlation matrix only allows you to use the Gaussian copula. So it's what you're familiar with as linear correlation. A correlation coefficient can range from -1 to +1. Negative correlations mean they're inversely related, positive means they're positively related. And so you can enter a correlation matrix and then add it to the distribution, or you can enter a copula and add that to the distribution. In either case, when you define the copula or the correlation matrix, there is an attachment where it can say attach it to the two distributions. Alternatively, you could enter the distributions without any correlation, highlight them, and then go to define copula or define correlation matrix, and it will get attached. The third way to do it is to define the copulas or the correlation matrix separately, and then go back in and change the distribution to add in either risk Cormat for the correlation matrix, or if you want to add the copula, you could change this to risk copula 2, let's say, copula, and instead of new matrix, a name. You could either use copula 1 or copula 2. You could do copula 1, first position, and then change this to risk copula. Name is I think I did 2. Let's do 2. Second position. Let me make sure about it. Oh no, I did copula 1. So that does the same thing. If you want at risk to add the copula automatically, you want to use that attachment editor or define your distributions and then highlight them before you go to define correlations, either the matrix or the copula, and then it will automatically attach it. I recommend that just because you don't have to remember how to do this. The time that I usually enter it by hand is if you built a model with no correlation, then you want to say, okay, what happens if I correlate them? You've already got the distributions in your spreadsheet. The easiest thing to do is highlight the ones you want to correlate and then define the correlation matrix or the copula in order to then have them not vary independently anymore. So if you've already built the model and you want to then introduce correlation, you will probably be entering it, you'll probably be highlighting it and then defining a copula to go on top, or you may just simply define the copula separately and then go in by hand and enter it, add it into the distribution. So the copula is represented by adding it into the distribution as another argument, and it could be any kind of distribution. So this one could be, instead of a risk uniform, it could be a risk normal. It could have a mean of, let's say, 10 and a standard deviation of 5. So it can be a completely different kind of distribution. And if we're using copula 1, let's see what happens if we make them perfectly correlated. Oh, actually, I think I need to start on one of those cells. Otherwise, define them as outputs, and then you can look at it that way. But let's look at the scatter plot. So you don't see a straight line, you see this curve, which is an S-shaped curve. There's no scatter, so they are in fact perfectly correlated. But the reason you don't get a linear pattern is that the uniform distribution is ranging from 0 to 5. Notice the value for the second distribution, which was a normal distribution, has a wide range of values here, actually from -25 to +25, and there's a perfect correlation pattern, but it's not a straight line because of the nonlinear form of the normal distribution. So there's nothing that requires these to be uniform distributions or be the same type of distributions. Any distributions can be correlated, and the degree of the correlation will come through reflected in that distribution. Now, all I've looked at so far are normal Gaussian distributions, which is linear, what we think of as linear correlation. But it's important to realize that the correlation patterns can be more complicated than that. A good example of this, let me use one from the book. This was kind of an important example. It really is at the heart of the Great Recession. Let me get it here. City home prices for. This has an index of home prices from 1990 to 2018, so 28 years of monthly index of home prices in Seattle and Las Vegas. And what you really want to do is look at the month-to-month change, ignore the fact that Boston is there right now. And so if you have Seattle and Las Vegas, here are the month-to-month changes. I use the continuous version of a percent change, the natural log of one value divided by the other value. So what we have here are monthly changes for these two. So here we have data, and are the two cities related to each other, or are they independent of each other? Actually, before the Great Recession, Alan Greenspan, who was head of the Federal Reserve at the time, was famous for saying real estate is essentially a local market. And so the belief was that real estate in different markets was unrelated to each other. Some could go up, some could go down, and this was the reason why if you pooled mortgages from a lot of different markets together, the risk could be in theory quite low because the markets were uncorrelated. You have mortgages in some markets where it's going up and others it's going down, and that diversification protected you against risk. I highlighted these two monthly changes, and when you go to define correlations, in this case we would fit a copula. You can choose what types. There are two methods. Basically, maximum likelihood is the one that you most of the time would want to use. And just click OK. You get a window showing the various things, how they fit. The Gaussian copula is not the best fitting one. The Clayton copula actually is the best fitting one, and it's a little hard to tell from this picture, but not that much. If you look at it, you'll notice the points in the bottom left are kind of closer together than the top right. The Clayton copula is a particular type that captures a pattern where there's correlation that's stronger at one end of the distribution, either at the low end or the high end. And in this case, in housing prices, it's at the lower end that they were tightly coupled. At the high end, they're not very correlated. So the correlation is weak when prices are going up in these two markets. The correlation becomes fairly strong when the prices are going down. And the further they're going down, the more strongly correlated they are. So think back to 2007. All of these real estate markets had had a period of over 10 years of sustained growth. Prices were going up pretty much everywhere, but the rate at which they were going up was pretty much unrelated, which is why Greenspan could say that there's no correlation, that real estate markets are local. However, in 2008, 2007, when they started going down, when they went down steeply, they went down pretty much everywhere together. And so all of these assets that were based upon the theory that real estate markets were unrelated and independent of each other were suddenly very risky, because when mortgages were getting defaulted on in some markets, they were also being defaulted on in the other markets. There was no diversification protection. The Clayton copula actually is picking up that pattern, that they're negatively related. They're strongly correlated when they're going in the negative direction, the bottom of these distributions. So the Clayton copula is the best fitting one. I would use that. And so these other types are available. Some of them are not available for mathematical reasons for this particular form of the data. So Clayton copula fits best. If you fit it to this data, you would then say write to spreadsheet. You can either create as an unattached copula and then go in and measure distributions for these two and then add the copula to it manually, or you can attach it to, if you've already fit the distributions, you can attach the copula to it right now, and at risk will do it for you. For an unattached copula, just say where you want to put it, and it puts in a copula just like we defined before, same kind of, looks the same basic way. You can't interpret this parameter. It has to do with the mathematical form of the Clayton copula. But now if you went and fit distributions to the monthly change in Seattle prices, monthly change in Las Vegas prices, you could then point those distributions by adding in risk copula. It would be copula 2. And you would do comma 1 for the first city and comma 2 for the second city. There's one other method available when you're fitting copulas, and I added in a third city, Boston, and with Boston, I calculated the monthly changes. They have to be in contiguous columns for this, but you could highlight all 3 of these. And I'll show you 2 options here. One is you could fit a copula, and some copulas are only available for 2 variables. When there are 3, it automatically selects the ones that you could use. Do that, comes out to the Clayton is the best fitting copula. And I think from this vision, with the picture somewhat smaller, you can see how concentrated it is on the bottom left. All 3 of these cities is a strong correlation pattern when it's in the downward direction near the low end of these distributions, not much correlation in the upper right. So again, you can do that, fitting it to the 3 of them, and it fits all the different types. Another option with these highlighted is to actually go to the distribution fitting window and do batch fit. And click fit. When you use batch fit, it creates another workbook. It has fit distributions to all 3. And it's also fit a correlation matrix underneath it, so you notice the correlations. I didn't include the names, so it's hard to tell which they are, but it was, I think, Los Angeles and Las Vegas, Seattle and Las Vegas, correlation of 0.527, which is moderate correlation. Notice that Boston was a lot lower correlation to either of the 2, to the Seattle or Las Vegas. Fairly weak correlation to Boston, which is a completely different part of the country. So the correlation matrix is there, and you also notice if you look at the actual, well, let me just see that these are the all the distributions for each one separately, but let me go back into the fit summary here. I guess you would have to manually attach the correlation matrix. It's here, but if you now wanted to simulate some months here, you could do well, actually, let me do it this way. Copy this, paste it in here. Actually, I'll copy these two also. So in simulate a month, you would use that, but if you want to use this correlation matrix, you would add in risk format. And I guess you'd have to add in the range here, since it doesn't have a name, B20 to D22. And comma 1, position 1. And then you'd add in the correlation matrix for the other two, and position 2 for this one, and position 3 for this one. So it's fairly automated. The thing to realize about this is that this matrix is only for linear correlations. So the Clayton copula would not be fit using batch fit under distributions, since it's only allowing for linear correlations. Whereas if you do the fit under this fit copula to the 3 data series, it will examine all the available types of correlation patterns, which is important here because the Clayton is a much better fit and has an important difference to just linear correlation. But batch fit does allow the correlations to be fit at the same time as you're fitting distributions. It just limits it to only one type of copula being fit. I should mention in this particular data, and the book does mention this, it's really tough, but and there is some correlation over time. So in reality, you would want to use a time series fit to this. And there is a batch fit for time series data, which will also estimate correlations. So this data, we can look at it in the next chapter, and it's even easier to fit the correlation pattern with fitting the time series models. But if you want to treat it as just values and fit a distribution to it, batch fit will give you some of the correlation between them, but not all types. In this case, I would much prefer to use the Clayton copula because it's a much better description of what's going on in the state. One other topic about using correlation matrices is, and this is an example in the book of these various ways in which cockpit systems can have failures. And so as the book describes, I mean, these are using exponential distributions for each of these with a mean time to failure of a certain number of hours. And we have a lot of different systems, 35 of them in the cockpit, each with its own kind of failure possibility. The exponential distribution could be used to model each of the separate failure probabilities. In all likelihood, these systems are not independent of each other, though, so you'd want to correlate them. And I've done that by adding in the risk format correlation matrix, and I've defined the matrix out on the right. I put in all of the different systems, and then I entered by hand, although so you'll notice they're all 0.8, these correlations. I just It was easy to enter a 0.8 and then just copy it. That's what I did. In reality, you probably have different correlations between different sets of these cockpit systems. So it might be that there are a few of these that have to do with communications that might be tightly correlated with weakly correlated to the other systems, and other sets of subsystems might be tightly correlated with each other. So you might have a fairly complex pattern in this correlation matrix. And when you get a complex correlation matrix, it's entirely possible, in fact, I'd say it's likely, that it will be an inconsistent correlation matrix, meaning that when you say that the first system is tightly correlated to the second, and the second is tightly correlated to the third, but let's say there's no correlation between the third and the eighth, but the eighth is tightly correlated to the 15th, and the 15th is tightly correlated to the first, it's not hard to imagine that you're going to get correlation coefficients that are inconsistent with each other. So there's two things to prevent this. One is when you're defining the correlation matrix, which actually I think I can show you by highlighting it here. When you click OK, it automatically checks for whether these correlations that you've entered are consistent, and if they're not, it adapts them to the closest values it can find that is internally consistent. Put very simply, if you think about three inputs, you say 1 and 2 are closely correlated, 2 and 3 are, and 1 and 3 are not. It can't be. If 1 and 2 are closely correlated and 2 and 3 are, then 1 and 3 have to be, but you may not have thought that through ahead of time. So you may have entered the correlation coefficients you thought described it, and if you click OK, it will automatically adjust these correlations to something that is internally consistent. If you read in the manual, there's even a more sophisticated way to do this, where you can control how it adjusts the correlations by putting weights on them, saying that there are certain correlations you're more confident in than others, so it will only use the less confident ones to adjust those. The other option is to use another function, which you find under just see where it is. Oh yeah, risk correct format. So what this does, let's see if I can get the a valid correlation matrix. So you can highlight a correlation matrix, use that function, it will automatically adjust it, and then use the corrected matrix. That's essentially what iRisk is doing for you. If you just click OK, it automatically does that. But if you want to do it manually, you can highlight the matrix, then use risk correct format to get a corrected matrix that's internally consistent, and then use that, attach it to your inputs to impose the correlation. But remember, the correlation matrix here is only using linear correlations between them. You have to fit or define a different correlation pattern than using a matrix. You'd have to define an actual copula and choosing a different copula type. Once you choose the matrix, all you can enter in the matrix are linear correlation coefficients. Okay, there's one other very complex topic in chapter 4 about regression. I'm going to do a separate video on that. So this just handles the basic ways in which you can define correlation, add it into your simulation, or if you have data, fit the correlation to the data and use that with the distributions in order to capture the correlation pattern.